Okay, so here we have a circuit with some resistors and some capacitors in it, and we had a couple questions about the state of the circuit after the circuit has been connected for a long time, right? That's telling us that the capacitors are all going to be fully charged. So the first part is just a simple calculation of the total capacitance, right? So part A. We have two capacitors in series, and so if we look at the equation sheet, we see that 1 over C total is 1 over C1 plus 1 over C2, inverse, right? So we plug in our numbers, we get 1/12 plus 1/6 inverse. So 1/12 plus 2/12 is going to be 3/12. Oops, I realize I wrote something wrong here too anyway, right? This is, I've already done the inverse, so this is just C total, right? So 1/12 and 2/12 is 3/12. Invert that, we get 12/3, which is 4, and we notice our units are microfarads. Alright, so that's part A. Part B is a little bit tougher, but not a lot. The key is to recognize that when the circuit has been connected for a long time, the capacitors really don't do anything anymore. There's no current flowing across that path at all. So the circuit really just looks like this. That was a terrible resistor. Let me try it again. Right. Right? And that's a circuit that's really easy to do. Just because there's capacitors doesn't mean that that affects what the charge is doing after this long period of time. So we combine the resistors that are in series to get a total resistance of 30 ohms. And so then we know that delta V is I times R. The potential difference across that combined resistor is 6 volts. I is what we're trying to find. And R is 30 ohms. So the current I has got to be 0.20 amps, right? And because in this circuit there's no junctions at all, right? The capacitors don't actually provide a second path for charge to flow at this point. So that means that that's the current through every part, including the 10 ohm resistor that we're asked about. Okay, so part C. There's two different ways to approach this one, but they're both very similar. The first is you could keep the same circuit we just used, right? Because on a wire there's no potential difference between points on that same wire. The potential difference between points A and B, which are sort of on both sides of the capacitor, that's the same as the potential difference across the 20 ohm resistor. So if I use that circuit and that approach, what I want, really, is delta V like that. And that's pretty easy to calculate, especially now that we have the current, right? Delta V equals IR. So delta V equals 0.2 times 20, right? And that is 4 volts. The other way, right, that works. That's a fine approach. The other way is to remember that capacitors still have to obey the loop rule. So in the original circuit, right, this is supposed to be an OR. In the original circuit, we have resistor, capacitor, other capacitor, kind of like this. And if we take a loop around that path, we know that delta V is 0. So we have a positive 6 volts from the battery minus I times R from this top resistor minus delta V A, B, right? Because point A is right there, and point B is right there. and that has to equal 0. And since the only thing we don't know is delta VAB, we can still solve for it, right? Delta VAB is 6 minus 2, or 4 volts, right? Once again, it's the same answer, right? So either one of those approaches works. All right, on to D. This one is a little bit tricky, depending on how comfortable you are with capacitors, but we need to first combine the capacitors into one equivalent capacitance, which fortunately are already done, right? So this new circuit, this is 4 microfarads. Yes, there's a resistor part, the 20 ohm resistor, but we don't really care about that because it's not part of the capacitance. And so what we're trying to find is the charge on the plate right here, right? One of the plates gets charge Q, the other one gets minus Q. Right? So, how do we go about doing that is the question. Because we can find that, then we're going to be able to relate that charge to the charge on one of the original capacitor's plates. And we have to remember that we already found what delta V on this capacitor is, right? By the loop rule, there's a delta V of 4 volts here too. And so we can use the formula for capacitance. Q is C delta V. And so that tells us that Q is 4 microfarads times 4 volts, or 16 coulombs, not farads, microcoulombs. Okay, so we've calculated the charge on our total capacitance plate, but how does that then relate to the charge on the 6 microfarad capacitor that's really there? And the answer is that it has to be the same. And so here's why. Let me draw this whole thing back in the original. Right, that's our original circuit. If this plate here has a charge Q on it, because the potential difference here is also the same 4 volts, that means this has to be plus Q and this has to be minus Q down there. And so that means all the center can do is polarize. Oops. And so that means I'll get it right eventually. And so that means that since the center just polarizes, it moves an opposite amount of charge to the other plate. Right? So because the potential difference is the same, that forces the charge on the 2 outermost plates to be the same, which then answers the question of what's going on with the specifically 6 microfarad capacitor. And so the answer, right, in the end is just this right here. I didn't need to do any actual work at all. Alright, finally, part E. Right. So we're cutting the wire at point P after the circuit's been connected for a long time, and we're asking what happens to that potential difference. And the answer is that it remains the same. And the explanation is, I think, a couple different ways of approaching it. But the simplest is, after a long time, no current is flowing, right? Once you see that phrase, long time, that means no current, right? It's already fully charged. And if there's no current flowing on that branch, because the capacitors are fully charged, it's already as if the circuit is broken, right? And cutting the wire doesn't change a thing. It just means that we can't later discharge the capacitors, but they aren't trying to do that right now anyway. And so since there's already no current, then cutting the wire doesn't change the current at all.